Welcome to our Class 17 pre-lecture. Today we are going to be delving more into the qualitative behaviors of linear constant coefficient homogeneous systems that are 2 by 2 specifically. Now, why do we focus on 2 by 2 systems? A lot of the practical applications that we need to look at do end up being 2 by 2, or if they're higher dimension, we can often reduce to 2 by 2. And these, of course, are easy to visualize, and we will be talking about visualizing the solutions to these systems as well. Let's first talk briefly about the existence and uniqueness theorem that we have when we're dealing with a system of first-order equations as opposed to just a single first-order equation. You remember when we dealt with a single first-order equation that was linear in the normal form, our theorem told us that if the functions p and q were continuous on some interval, then the initial value problem would exist and be unique on that same interval. We can now extend to a system of first order ODE, except we have now just extended our solution space into higher dimensions. So now we have x prime is some matrix A times x plus a forcing function with an initial condition. If all the functions in the matrix A, which could be a function of t, and the vector f are continuous on some interval of time, then the solution to that initial value problem exists and is unique on the whole interval. We also learned that linear homogeneous differential equations have the property that a sum of two solutions is still a solution. This is the principle of superposition. Well, this is also true for systems of first-order linear homogeneous differential equations. Take a second and pause the video and convince yourself through this exercise that if you have two solutions, x1 and x2, of a differential equation, that the linear combination of these solutions to this homogeneous linear differential equation is also going to be a solution. Because both the operations of differentiation and matrix multiplication are linear, we can easily see that any linear combination of solutions to this ODE will also be a solution. Let's go to the next page. Here we have a theorem about the dimension of the solution space. Compare this to what we learned in lecture 11 when we dealt with a higher order single differential equation. What our theorem says is that of n first order ordinary differential equations is an n-dimensional vector space. The structure of the proof almost exactly follows the structure of the proof that we did in lecture 11 for a single higher order ODE. We first note that because the system of ODEs is both linear and homogeneous, the set of all solutions forms a vector space. Now, we just proved that any linear combination of solutions is also a solution, confirming that the set of solutions is indeed a vector space. Now we're going to prove that the dimension of that vector space has to be at least as large as n. And that's because we're going to be able to find n linearly independent solutions. The way we do that is to consider n different initial value problems where what changes in each problem is just the initial value. And in each case, we're going to let the initial value be one of our standard basis vectors. So by the existence and uniqueness theorem that we saw on the previous page, each one of these initial value problems has a unique solution. And we're going to denote that solution x sub I, where x sub I at initial time is its associated standard basis vector that was specified in our initial setup. Now we know that each one of these n solutions is linearly independent because the only way to combine them linearly and force them to be zero is to have the trivial solution. In other words, every coefficient must be equal to 0. So we have successfully shown that we can find at least n linearly independent solutions. The next thing we're going to show is that the dimension of the solution space can be no greater than n. We're going to let vector u be an arbitrary solution to the differential equation, any solution at all. So we have to have some general initial value vector at our initial time. But what does that mean? Then our solution u is going to be a linear combination of our previously found solution vectors x1 through xn. Why is that? Of course, each x sub I is a solution, so a linear combination of the x sub i's is also a solution, which we discussed. Putting statements 2 and 3 together, in other words, the fact that we can have no more than n dimensions and we will have at least n dimensions, tells us that the dimension of our vector space is therefore going to be exactly n. and our theorem is proved. Let's go to the next page. This means that even though there are infinitely many solutions to the homogeneous ODE system, once we have found n linearly independent solutions, we have essentially found all possible solutions to the system. Pause the video and work out this exercise yourself. For the constant coefficient case, in other words, where matrix A does not depend on time t, under what conditions will a vector of the form v e to the lambda t be a solution for some constant scalar lambda and some vector v? If we want to see what makes v e to the lambda t a solution, let's first take the derivative, which we know needs to be lambda v e to the lambda t. Now, in order to be a solution, we must make sure that this equals a v e to the lambda t. For that to be the case, we're going to need v lambda e to the lambda t equal to a v e to the lambda t. We can, of course, cancel the e to the lambda t's because those will never be zero. And what does that imply? That means that lambda v has to equal AV. But look what you've discovered. This is the necessary condition for VE to the lambda t to be a solution to our ODE, but this is also the definition of an eigenvalue-eigenvector pair. What we have seen is that if we want VE to the lambda t to be a solution, then V and lambda must be an eigenpair. But what does that indicate? If the matrix A is diagonalizable, then we know that it will have n linearly independent eigenvectors. We know that each eigenpair yields a solution to the ODE, and therefore a linear combination of all the possible eigenpairs will also give us a solution to the ODE. So with this approach, we have found another way to confirm that this linear combination of eigenvectors and e to the eigenvalue t forms the most general solution to the ODE system. Let's go to the next page. We have now seen two solution approaches in the context of a diagonalizable constant matrix A. With knowledge of the eigenvalue-eigenvector pairs of the matrix A, we can immediately write down the general solution to the ODE. If, in addition, we impose initial conditions, then we have seen that our initial value problem solution can be given by e to the AT times our initial condition vector x naught. In both of these cases, the coefficients Ci are determined by our initial state vector. But let's look at what that means when we look at the example that we started with a couple of lectures ago. Now, suppose, along with this ordinary differential equation system, we have general initial conditions, x1 at time 0 is alpha and x2 at time 0 is beta. We've already diagonalized this matrix so that we know we have eigenvalue 4 and eigenvalue 5 associated with eigenvector 2, 1 and eigenvector 1, 1. Now writing down the general solution and then applying the initial conditions will give us our unknown constants C1 and C2, and we end up with the full solution to the initial value problem. Alternately, we can directly use the matrix exponential, as outlined here. The matrix exponential times our initial value vector immediately gives us the unique solution to our initial value problem again. And notice in both cases, we have found exactly the same solution. Let's go to the next page to practice visualizing what these vector solutions look like. Okay, given this linear constant coefficient homogeneous differential equation with coefficient matrix A given by 0, 1, 1, 4, 0, let's walk through the steps of finding the eigenvalues and associated eigenvectors, using the eigendata to write out a general solution, and sketching a direction field. We are going to practice a lot more of this in class, but we'll do one example here. Using the standard techniques that you learned in your linear algebra class, we can find the eigenvalues 1/2 and -1/2 and their associated eigenvectors. Using this, the general solution is written as a linear combination. Finally, let's go to sketching our solution. We should ask what this solution form means when it comes to thinking about sketching solutions. We see that part of the solution will move in the direction of vector 2, 1, and grow at a rate e to the t over 2, while the other part of the solution is going to move in the direction of the vector -2, 1, and shrink at a rate e to the -t over 2. Let's go to this plot grid and plot what that might look like. I've put the solution here down below so we have it for reference. Let's first think about how to plot the 2, 1 component of the solution. That 2, 1 vector
will look like this.
And the eigenline extends with the same slope. The minus 2, 1 vector can be plotted like this. And its eigenline is also going to extend with the same slope. Now suppose C2 equals 0. That means that our solution only moves in the direction of 2, 1.
Since the magnitude of x increases as time increases.
We also know that we will be moving away from the origin as time increases. We will plot that here by putting arrows on the eigenline in a direction moving away from the origin. Suppose instead that C1 was 0. That means that our solution x moves completely in the direction of the eigenline pointing in the minus 2, 1 direction. And the magnitude of the solution is now shrinking as time goes to 0. So on that eigenline, we will identify the direction of the solution to be moving toward the origin. The next thing we need to think about is, okay, what happens when our solution is some linear combination of those 2 eigenvectors? Suppose I start somewhere up here. What's likely to happen is that I will be drawn first in the direction of the eigenvector to which I am closest, but eventually I will get drawn away to the other eigenvector to which I am close. Well, we're going to see something that looks like this, making the origin a saddle point. And we will talk more about that in class. That's it for today. We're going to have a lot of practice in class. See you there.